Container security and container hardening. Let's have a look. We recommend you watch our DoD case study segment before watching this video. So what is container security and what is container hardening? In DoD, we understood the importance of having reusable Lego blocks that can be shared across the department. This prevents massive waste of resources and redundant work. We created the Iron Bank, the centralized artifact repository, kind of a Docker Hub but more secure for the DoD. Check it out. By the way, it's open source and free. ironbank.dso.mil. Iron Bank is our container repository for hardened containers. We partnered with open source projects and commercial companies to harden over 1,000 containers. The beauty with containers is that they're designed in layers. So let's take a look at how we use container layers when it comes to incredible benefits to cybersecurity. The first thing we've done with Iron Bank is to create the base OS layer. That's a foundational base image for all the containers. We picked UBI, Universal Base Image, from Red Hat by first hardening UBI using things like SE Linux and different Linux settings to make it as secure as it can be. So this layer is now the base OS for all of the containers. And that layer is hardened thanks to automation and the proper settings, and of course scanned continuously as well. So now you have this base layer. That's the operating system that's used across all containers. Now let's say you're building a Java application, right? So in DoD we created another layer of base images, and we have multiple of them, right, for each programming language. So in this case, let's say we wanted to support Java applications, so we created an OpenJDK base image on top, inheriting from that UBI 8 hardened base OS image. So now OpenJDK is also getting hardened following the proper settings recommended for DoD for Java. So now we have this image that becomes the official base Java image for DoD, and that's hardened automatically and continuously updated. So now the beauty is, if you end up updating the base OS image of UBI, it automatically also updates the OpenJDK image. Now, if you have a Java application on top here, created by a mission team now, they can simply use the OpenJDK hardened image and inherit both the OS hardening and the OpenJDK hardening as well. So their work is much lighter. They only have to worry about their applications on top. And we do the same for every language. Now, if we have to update OpenJDK or update UBI, all of the containers across the entire enterprise get seamlessly updated. So we started with the bottom layer, the operating system base image of the container. We picked the universal base image from Red Hat, which is based on RHEL 8, but completely free and open source. We hardened that image by removing unnecessary bits and configuring it to be as secure as possible using things like SE Linux and various Linux settings. Now that base image can be used as the foundation for all other images. So if there is an issue with Linux, we can update that base image and all of the other containers will be seamlessly updated. Then we also built images for various programming languages so that each team doesn't have to support those. So for example, for Java, we built an OpenJDK base image based on the UBI hardened image as a base image, and we proceeded to harden Java as much as possible. Now, a team that's building a Java application can simply use our Java base image, which already meets the operating system and now Java requirements for DoD. It's all inherited. More importantly, if there is a 0-day in the base OS image or in Java, we can update that single image and automatically all images on top can inherit that change immediately. No need to reach out to thousands of teams to tell them, hey, you need to update Java. We do the same for databases and various DevSecOps and cyber tools to be able to have already hardened images for various teams to consume. So now you can imagine that by using this concept of layers, if there's a 0-day in Linux on some TLS crypto, we can immediately update the right base image, and this will in turn update every single container across the stack. Thanks to our Cattle approach, killing containers every 4 hours, they will self-update every 4 hours and patch themselves across the enterprise. No more manual patch management. This drastically reduces your attack surface and the complexity of managing patches across teams. So let's take a look at what it takes to harden containers in DoD. First, we work with the community or the vendor to automate that process and make it as painless as possible. We rebuild all images from Docker file. We don't accept binaries. We do that because first we need to be able to rebuild the container if a base image is changed, but also to be able to swap the default base image from their commercial base image to our DoD approved universal base image that we already hardened. We then look at a few security critical things first. We use 2 container scanner technology with Anchor and Twistlock to scan the containers for known CVEs. We found that using only 1 scanner wasn't good enough due to false positives or false negatives. So we combined the results of the 2 scanners into our vulnerability assessment tool. This tool was designed to provide a UI for vendors to justify the CVEs and findings so they can document how they plan on mitigating and addressing those CVEs. It's also used for our team to review the findings and approve or reject the risk so we can understand exactly how secure or insecure some container would be. We work with vendors and open source communities to address or mitigate all high and criticals at the very least. We also leverage Anchor to create Dockerfile rules to look for bad pattern in container Docker files, such as using environment variables to store keys, for example. Anchor also generates a software bill of material, SBOM, of the container as well. If you missed our video on SBOM, check it out. We have several rules that were created based on the DoD container hardening guide. Check it out. We want to make sure that all base images come from our trusted registry so that we are tracking all dependencies and their provenance and integrity using signatures and checksums. We look at enforcing some basic practices with containers as recommended in the CIS Docker benchmark, with things like not running containers with elevated privileges, not sharing the host namespace, emitting logs to std out so we can collect them across the stack thanks to our sidecar injection for logging and telemetry, using TLS approved encryption bits, removing unnecessary packages and services. Once that process is completed, we sign the container with a DoD trusted key and it is published for consumption inside of the repository. If the image is updated by the vendor or the open source community, we allow the image to self-update as long as there is no new CVE. If there is a new CVE, of course, they have to justify the new CVEs and we have to manually review the CVE to see if we want to approve it or not. Of course, new vulnerabilities are discovered multiple times a day, so the scanner process and hardening process isn't a one-time thing. It is continuous and at Iron Bank enforced every 6 hours. You cannot let security become stale. We certainly don't want to drift from commercial source of truth, so the goal of Iron Bank is to stay in parity with the commercial release cycles. Your container also inherits risk from the container host, your Kubernetes nodes, so it's essential to harden your nodes and their operating systems. For that, take a look at the DoD Kubernetes STIG and the CIS Kubernetes benchmark. Our critical security capabilities also lies in runtime with solutions like Twistlock or Aqua or NuVector, so you can continuously monitor the behavior of containers thanks to AI/ML prevention capabilities to automatically kill and alert your teams if a container starts to behave like something is never done before. So securing a container isn't just about pipeline checks. Those are important, but the fact is scanners will not detect malicious code. Malicious code in nature are not detected by scanners. That's what you've seen recently with attacks on like SolarWinds. Only runtime security can detect and prevent those thanks to moving target defense, continuous monitoring with behavior prevention, and zero trust. Check out our segment on the 3 pillars for modern cyber posture to understand how this plays together. Iron Bank and this process is one of the most important contributions to open source by the US government and the DoD. Platform One invests about $60 million a year in its open source work with Platform One Big Bang and Iron Bank. So check it out. It's all open source. There you have it. Container security and hardening is essential for your cyber posture and to streamline your patch management across your organization. Container layers and hardening will enable your development teams to reuse components and, more importantly, enable your cyber teams to enforce and secure things centrally, but spread them across teams immediately and effectively. It's important to realize that scanning and pipeline hardening isn't good enough. Many commercial organizations get breached, and the chance of your organization inherited malicious code through one of those applications is important. So at the end of the day, scanners are not capable to detect malicious code. So continuous monitoring and the 3 pillars of modern cyber defense are critical to ensure you mitigate your risks.